Welcome back, everybody. Hope everyone's doing okay. Here, let me let in a couple more people. All right. We will continue with chapter 8. Any questions up to this point? No? Okay. Well, this is where we ended up. We were talking about naming organic or ionic compounds. Okay. And we had just finished talking about polyatomic ions and writing the formula for them. And the main takeaway with polyatomic ions is to remember is that when we keep them as a packet, as a unit, if we need more than one, we put a parentheses around it, just like the first example there where you have magnesium and hydroxide. We need 2 hydroxides because each hydroxide has a -1. And the magnesium is a group 2 element or group 2 metal where it loses 2 electrons, has a +2 oxidation number, and therefore we need 2 hydroxides. Okay. The same with calcium and nitrate. We need 2 nitrates, so on and so forth. Okay. Well, now that we can write the ionic compounds, we need to learn their particular names. And the name depends, and here we're talking about ionic compounds first. We'll get into the covalent compounds. But the thing about covalent, the naming of covalent and ionic compounds with respect to the partner, if you will, the non-central element. And I say this, broadly because in ionic compounds, you have the anion, okay? Like the chlorine becomes chloride. Well, that name continues when you deal with covalent compounds. It's still called chloride, even though it's in a covalent compound. And that's respect to the negative oxidation number for species. Okay, so the name depends on whether the metal is a fixed or a variable charge. When we say fixed, there's 16 elements, 16 metals that 100% of the time, their particular specific oxidation number or /charge. Everybody else, all the other metals are variable, and therefore we need to use Roman numerals to describe which one we're dealing with. Okay, like copper. Copper can be copper 1 or copper 2, depending on how many it has lost with respect to electrons. This one here, pretty self-explanatory. I just explained how the anion changes its name. So chlorine, the ion becomes chloride in sodium chloride. Okay, well, here we have the KBr. K is potassium. Br, as we know, is a bromine. However, it is in the form of an ionic compound here. So like chlorine, it becomes, we change its name to bromide. Okay. The oxygen, here we got magnesium and oxygen. Name, still magnesium for the metal part, but the oxygen becomes oxides. So its name is magnesium oxide. Now, bear in mind, as I stated, when we get to covalent compounds, the bromide, the oxide, the chloride, that part of the name continues to be called in that form when we get to covalent compounds. Here we have calcium. Now, you might be tempted to think it's diatomic fluorine, okay? But remember something, is we have fluorine here at first glance with a 2 thinking is diatomic, but we have a metal in front of it. Okay, so that tells you, there should be a flag to tell you that is fluoride, calcium fluoride. Okay, not fluorine. And then we have here lithium. And then sulfur becomes sulfide. So lithium sulfide. And then, of course, Ag, not to be mistaken with Au, which is gold. This is silver. And Cl, again, chloride. So we got silver chloride. Notice up to this point that we do not use any prefixes. And that is the thing about ionic compounds. There are no prefixes involved. Prefixes like, di, tri, etc. None. And so this one, calcium fluoride, would not be called calcium difluoride. It would be incorrect to do that for ionic compounds, okay? Now, sometimes, occasionally, if you look at labels of your products that you use on an everyday basis, they will use prefixes for ionic compounds. So why they do that, I don't know, but that is not the correct name. We don't use, for example, this would not be for lithium sulfide, would not be dilithium sulfide. Now, it might be dilithium crystals if you're on Star Trek, but not ionic compounds. Okay, no prefixes. Second of all, notice for calcium here, all the metals, we did not use no Roman numerals in all the names here. Okay, because these metals that we worked with here are part of the 16 with exact oxidation numbers, exact charges. And with those 16, we don't use no Roman numerals. So potassium would be incorrect to say potassium Roman numeral 1 bromide. Okay, so no Roman numerals for the 16. It is the other metals, all the other metals that we require Roman numerals. All right, for polyatomic ions. Okay, now this can be a challenge sometimes, but I want you to look at this, for example. So you look at this formula, you look at it, disregard the name, we know it's called sodium nitrate, but if you see that, you see obviously you got Na for sodium. And then you see the nitrogen, and you might think, possibly nitrite, okay? You might think that at first, but right immediately next to nitrogen are oxygens. And so when you see nitrogen immediately followed by oxygens, definitely not IDE, it's going to be either an ATE or an ITE. Okay, we know it would be the Ni because of nitrogen, so it's going to be something NiTr. It's going to be something like that, and we don't know at this time. Well, which one is it, A or I? With time, you get to recognize that three of them. 3 oxygens would be the nitrate, okay? But in the beginning, since we're learning to do this, you recognize you got nitrogen, oxygen, it's a polyatomic ion. I direct you to, clear this up here, direct you to the polyatomic ion table on the periodic table on the far left. Notice the NO3 is the nitrate. The NO2 is the nitrite. 1 less oxygen is the ITE. Okay. So let's elaborate more on that nitrogen, which would be true not only for nitrogen, but for sulfur and phosphorus and so forth. We see here that we have N, which is the element nitrogen. Okay. Now, we know it's in group 5, and when it becomes an ion, still we have the single element nitrogen. Okay, but when it becomes the ion, its name becomes nitride. Okay, now, when the nitrogen is bonded to an oxygen, and in this case, specifically 3 of them, and it has a negative charge, it is a polyatomic ion. And its name becomes nitrate. And there's another species with one less oxygen, with two of them, still with a negative, and that becomes nitrite. Okay. These are the polyatomic ions. This one is the single ion, and obviously this top one is the element. Okay, so polyatomic ion, two of them, the ion with the nitrogen all by itself, and the element. And you'll see also the same thing happens with sulfur. You got sulfur. Okay, sulfur is in group 6. When it becomes an ion, it becomes sulfide. Sulfur all by itself. Sulfur can also, the ion can bond, sulfur can also bond with 4 oxygens and form the polyatomic ion. And guess what? It is the sulfate. And if it's one less oxygen than the sulfate, then that is the sulfite. You see the little trend here you can see with all of them? Okay. All right. Let me turn this up a little bit. So we have here potassium, and then you see phosphorus and oxygen. So as I was working with nitrogen, the same is true with phosphorus. You might think phosphide, but right immediately there, right next to it is oxygen. So it is bonded to the phosphorus. Okay, it's following the phosphorus immediately, and there's 4 of them. So that should direct you to the polyatomic ion table, and you'll see that it is called phosphate. K is potassium, and you'll also notice that the phosphate ion has a -3 charge. So hence, that's why you have 3 potassiums, because each potassium is a +1. Okay. The next one, it has a parenthesis. So a parenthesis should alert you to the fact that you have a polyatomic ion. So automatically you look and see you got oxygen and hydrogen. You go directly to the polyatomic ion table, look for oxygen, hydrogen, polyatomic ion, and sure enough, there you go. OH, and that's called a hydroxide. All right, so that is the name for what's inside the parentheses, hydroxide. And the metal is calcium, so basically its name is calcium hydroxide. Okay. SO4, analogous to what we did with phosphorus and nitrogen. Here we have sulfur, which we might think sulfide, but note that we have immediately adjacent to the sulfur 4 oxygens. So that indicates polyatomic ion. Go to the table, look for SO4. Okay, you'll find it to be called sulfate. And therefore, Z is zinc, and it's a real straightforward name, zinc sulfate. All right, so let me clear this up here. So the variable charge metal ionic compounds, note that here, again, potassium, calcium, zinc, those metals are part of the 16, so 16. We know their oxidation number 100% of the time, hence we don't use Roman numerals. For the Roman numerals, we have to, for metals that have variable charge, we have to figure out what charge they have first. So, you see a metal, you see Cu, it's copper. You go and you find out, first thing you should ask yourself, are they part of 16? And in this case, obviously it's not, because we're talking about variable charge metals, but let's say you didn't know that. but you knew where the 16 were, and copper is not of that list. Therefore, that should flag you to say, I need to use oxidation Roman numerals. The question is, which one? Okay, so we back calculate. That's how we do it. Because remember, is number of cations plus number of anions for 99% of the compounds equals 0. Okay. A more broad equation would be the charge of compound. And now use an example why that encompasses a lot more examples. All right, so we have copper, Cul2. What we do know is this, based on the formula we're given, that the molecule has a charge of 0, okay? Copper, we don't know what it is. It's variable, okay? And so that is the cation. So it's plus the number of anions. Now we know that we got 2 chlorides. And what do we know about the chlorides? Well, each chloride is a -1. And so our equation is copper plus 2 times -1 equals 0. Or copper minus 2 equals 0. Copper must equal a plus 2, okay, in this format. Therefore, the name for this compound is copper, Roman numeral 2. All right. Okay. See how fairly straightforward it is. You're always going to know. See, this is an equation of 3 variables, 3 unknowns. You will always know 2 of those 3 unknowns. Okay. And here, the charge equals 0. But you could have an example, which you do in the homework, where the molecule itself may not be equal to 0. It may be charged. It could be a polyatomic ion. Polyatomic ions don't equal 0. Let me give you a quick example why this other equation, I wrote with number of cations per anions is equal to overall charge of compound, could be used a lot more effectively. Let's take, for example, the polyatomic ion sulfate. Sulfate has a -2 charge. Under these conditions, we can calculate what the oxidation state is for sulfur, okay? Because we know what oxygen will always be. Oxygen is always a -2, okay? Be it ionic compound or be it covalent. And so we can write this, sulfur plus 4 oxygens, each one with a -2, equals, guess what? -2. That is the charge of the polyatomic ion. You see how this one here is a lot more broad as far as encompassing the multiple different scenarios. Yes, the majority of them are equal to 0, but some may not. So I got an equation here where I got S, sulfur, minus 8 equals -2. We solve for sulfur. Sulfur is simply 8 minus 2 equals 2 equals 6, okay, +6. So under these conditions, the sulfate atom has a +6 oxidation number, okay? All right, so that's how we use this more broad equation. There are some homeworks that they give you hypothetical problems, hypothetical compounds where you're being asked to calculate the charge of an atom. So, you could say something hypothetical, X bonded to, say, 4 fluorides, and it has an overall charge of, say, -2. Well, you can calculate what the oxidation number is for X, the hypothetical element, okay, using that broad equation. All right, so after all that, we figured out that copper must be a +2, so its name would be written as copper, Roman numeral 2, uppercase, chloride. Okay. Let's take a look at this one. All right, so lead, we don't know. But we do know that the oxygens, as I stated, have a -2 each one. So we got a lead minus a -4 is equal to 0. So lead, under these circumstances, must be a +4 oxidation number. Okay, that means the name for this compound will be lead, Roman numeral 4, oxide. Okay, nickel is not part of the 16 variable oxidation. The bromides each we know they're -1. There's 3 of them. Okay, and so we got nickel -3 equals 0. So that means that nickel is equal to a +3. So we'd be using nickel, Roman numeral 3, to name that particular compound. Okay. Manganese, the sulfate. Okay. This is the polyatomic ion, SO4. We know from the table it's got a -2 charge. That infers that Mn, manganese, must be a +2. Okay. So therefore, its name is manganese, Roman number 2, sulfate. Okay. Copper. Here again, we have a NO3 polyatomic ion. Each one is a -1 charge. And so this copper must be copper 1. And that's, yes, copper, Roman numeral 1, nitrate. Okay. Don't forget, use Roman numerals. I know you'd be tempted to use, I keep saying Roman numeral 4, Roman, what I mean to say is Roman numeral IV. Okay, so it's not, would it be correct to say lead 4 oxide? Okay, use the Roman numerals. Roman numerals. All right, and then we have CO, which is cobalt, and then we got nitrogen. Guess what? All by itself. There's no oxygen next to it. Therefore, it is the ion. It is a -3, the nitride. And so cobalt under these conditions must be cobalt 3. And so we call it cobalt, Roman numeral 3, nitride. Okay. Now, this is a little more challenging, but let's break it down. Okay, we have iron, 2 of them, and then in parentheses, guess what? We have a polyatomic ion. So go to the polyatomic ion, and you will see that table. The table, it's a -2. That's the carbonate. And that superscript tells us that we had 3 of them. Okay. So overall, we have a -6 for the carbonate. The iron, we don't know what that is, but we have 2 of them. So we have 2 iron -6 equals 0. Okay. So let me rewrite this down here. We got 2 iron -6 equals 0. Again, the reason we have 6 is because the subscript tells us we have 3 of the carbonates, and the polyatomic table tells us that the charge of the carbonate is a -2 for each one. So we got a total -6. So we solve for iron. Okay, so we add a +6 on both sides of the equation, and we end up with 2 iron equals 6. And obviously now we want to isolate iron, so we divide through by 2. And iron is equal to a +6. 3. Okay. Iron is equal to a +3 under these conditions. So total, we have 2 iron 3s. It gives us a +6, and then we have a total -6 for the carbonates, and that, guess what, is equal to 0. So that must be correct. So therefore, our name would be iron, Roman numeral 3, carbonate. Okay. And guess what? If you look at the subscripts of the anion, 3, that is the charge of the cation. And if you look at the subscript of the cation, that is the charge on the anion. So at a glance, you can just look at the formula and right away determine whether you're working with iron 3 or that, for that matter, iron 2. Okay. Because iron 2 would be, the formula for iron 2 would be FeCO3, right? Because we know the cobalts each have a -2. That implies that this iron has to be a +2. This would be iron, Roman numeral 2, carbonate. Which is quite different as far as chemical properties than iron 3 carbonate. So we got two different compounds completely. All right, well, I'm going to give you the names of these, and you might, here's the answers already. First one's SR, strontium, and OH is the hydroxide, polyatomic ions. So basically, strontium is a group 2 metal, so it's a +2 charge. And hydroxides are -1. We need 2 of them, therefore we have the formula SR, parentheses, hydroxide. Okay. The name for AuCl3, well, Au is gold. Okay. Each chloride is a -1. We have a total of -3. That means that gold in this state must be a +3. Hence, we use gold, Roman numeral 3 chloride. Okay. Zinc is one of the 16, always has a +2. Oxide, as we stated, always has a -2. Simply put them on the 1-to-1 ratio because we got a +2 and -2. And the simple name, zinc oxide, no Roman numerals because zinc is part of the 16. Okay. This is the polyatomic ion phosphate. Okay. And this is barium. Okay. So the name is barium phosphate. The formula we have to put together, find a common number because the barium is a group 2 element, it's a +2. The polyatomic is a -3. So we have to find a common number, which is 6. So we need 3 bariums and 2 phosphates. And that's why our subscript for barium is a 3 and the subscript for phosphate is a 2. Okay. So we have sufficient negatives to cancel out the positives. Lithium is a +1. It's in group 1, so it will have a +1 charge. The sulfate, I made a mistake. I said sulfate because I made a common mistake thinking SO something, thinking sulfate, but this is only 3 oxygens. So double check on the polyatomic ions. You'll see that SO4 is sulfate and the SO3 is a sulfite, ITE. Okay. Here's the name right there. And it's lithium sulfite. We need two lithium ions because each lithium is a +2. And excuse me, each lithium is a +1. We need 2 of them. Each sulfite is a -2. That's why we have a lithium subscript 2. Okay, we have another example here of dissimilar charges. where the aluminum ion will be a +3. It's a group 3 element. Sulfur becomes sulfide, which is a -2. All right, so our common number here is 6. So I need 2 aluminums and 3 sulfides. Okay, and our formula now is Al subscript 2, sulfide subscript 3. Okay, we have total of 6 total negative charges and total of 6 positives. The name is simply aluminum sulfide. Again, no Roman numerals because aluminum has an exact oxidation number. And here, number 7, they just want the name. Okay, we got a parentheses. Okay, so that's a flag. I got a polyatomic ion, and it's an NO, so it's either a nitrate or a nitrite. So go to the table. And once you go to the table, you see that each one has a -1 charge. The nitrate is -1, and you got 2 of them. So that infers you got a total of -2 charge from the nitrate. So that means that the copper has to be a +2. Okay, so then we use Roman numeral 2 to name it. So it's copper, Roman numeral 2, nitrate. So whenever you're either using the name or given the ions to write the formula, or you got the formula and go back to write its name, put everything into ionic form. So you know how much of each we need for them to come together properly. That because, like I said, 99% of the time, the final charge on the molecule is 0. You can notice over here that everything here is no charge overall. It's all net 0. So we have to add enough cations and anions in the molecule to cancel each other out. All right, so here's another one you might try. We got sodium nitrite. Go to the polyatomic table, and we'll see that it's NO2 and 2, and each one's got a -1. Okay, sodium, its ionic form is always a plus +1 charge. It's in group 1. Okay, so hence our formula is a simple 1-to-1, 1 sodium ion, 1 nitrate polyatomic ion given here. Okay, nickel, Roman numeral 3. What that tells you is you're using the +3 oxidation number. Oxide always has a -2, always. And so we have a disparity here between a +2 and a -2. So we find a common factor, which again is 6. So that means we need 3 oxides and 2 nickel +3s. So our formula is Ni Roman numeral subscript 2, O subscript 3. Okay, magnesium is in group 2. It has a +2 charge. And iodide each is a group 7, so in ionic form is a -1. So we need 2 iodides. Hence our formula is MgI2. And then cyanide, that is a polyatomic ion, Cn, -1 charge. Just in our polyatomic ion table. The aluminum, always a +3. It's in group 3 metal. Okay. And so that means that we need 3 cyanides for each aluminum ion. Hence our formula is aluminum Al parentheses Cn and parentheses subscript 3. Okay. All right, so that is for ionic compounds. Okay, now the key thing to take away from here is 1, no prefixes for ionic compounds. So this would not be called aluminum tricyanide, just aluminum cyanide. Magnesium iodide would be not magnesium diiodide, but just magnesium iodide. So no prefixes for ionic compounds. Second of all, the takeaway for ionic compounds is put everything into ions when you're starting to write formulas. Put them into ions so you can make sure you put them together in the correct number of cations and anions to end up with this overall zero molecule, okay? The polyatomic ions, you need more than one. Use parentheses. Also, they have their own specific name. It doesn't change, the polyatomic ions. It is just the anions, the nonmetals by themselves that the name changes. So oxygen becomes oxide, sulfur becomes sulfide, etc. Okay. So, but when we get to covalent molecular compounds, remember by definition, these are compounds that are only nonmetals, That's it. All right. And so we don't really form ions here. And so we're not really talking about charges. So I use the term oxidation number because that represents, remember, for covalent compounds, we do talk about partial positive and partial negative. Whereas ionic compounds, we talk about a full positive or full negative, a full charge. And so we can't really use the term charge for covalent compounds. So we use the term oxidation number. And so unfortunately, we interchange oxidation number and charge, but I'm doing my best to just use oxidation number overall to apply to both covalent compounds and ionic compounds. Now, with respect to prefixes, yes, these are the ones that we utilize. Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. And occasionally, you may occasionally see nona, nona for 9, and deca for 10. Okay. Now, how do we name them? Okay, for the first nonmetal compound or element, we put here in green. It may or may not have a prefix. If there's no just one, we just give it a name, whatever it is, whatever the element is. Okay. Now, for the other nonmetal partner, it may have a prefix. And we do change the last name to "ide," just like oxygen in the ionic compounds gets converted to oxide. We maintain that naming for covalent compounds, okay? All right. And if the first metal, which is the central atom, no, I shouldn't say metal, if the first non-metal or the central atom is all by itself, we just call it whatever the name is, but we don't put the prefix mono, okay? Just unless there's more than one in the first element, then we use the prefix di, tri, whatever the case may be. For example, this one I've used quite often, everybody knows what this is. We see carbon all by itself, so it's just simply carbon is the first one. 100 times, 99.99% of the time, the first nonmetal is a central atom, and then whatever follows is bonded to the central atom. Then we have carbon, so I would, break it down with respect to the name. First one is carbon. Okay, there's only one, so we don't need mono for the first one. If there was two of them, it would be di, but there's only one. Then we have oxygen. That name does not change with respect to ionic or covalent. It is oxide. And then we have two of them, so therefore we put a prefix in front of dioxide. So we have carbon dioxide, okay? This one, similar scenario. Okay, first one is carbon. Okay, and then we have oxide, but we only have one. So here we use the prefix mono and take out the O off of the mono, and you have monoxide. Okay. So when you add prefixes, if you have two vowels, the prefix, the vowel and the prefix is removed. Okay. So for example, let's say the prefix you're going to use is penta, and then it's an oxygen. And so what you do when you combine them, the A, because you got an A and an O, both vowels, and we write pentoxide. Okay. Yes, sometimes I'm guilty of this, and I forget it to take the A out, and in the slide I forgot to take the A out. Some of them. So bottom line is, if you don't take the A out, I'm not too concerned about it. It's not the end of the world. All right. So this one, mono, and then plus oxide. You can see how you got to drop the O off of mono. I got two vowels. Okay. And so that's your English lesson for today. All right. Here we have P2O5. All right. So if we go about it, my suggestion is this: write the parent name first and then come back and add the prefixes. And so what we have is phosphorus. Okay. And oxide. So phosphorus oxide is the parent name. And now we come back for the prefixes. We got pentoxide, PT, I dropped the A. And then we got di for two of them, two phosphorus. You've got 5 oxides and 2 phosphorus. And so its name, okay, let me clear this, would be without the A after the pentoxide. And so diphosphorus pentoxide. Okay, here we have again parent name. P is phosphorus, F is fluoride. So phosphorus fluoride. There's only one phosphorus, so we don't have to add a mono. Okay, and then there's 3 fluorides, so we add trifluoride. Okay, trifluoride, phosphorus, trifluoride. I and fluoride bonded together. In fact, 7 of them. So it's iodine fluoride is the parent name. Iodine fluoride. 1 iodine, so we leave it as iodine. And then there's 7 fluorides, so that becomes iodine heptafluoride. Notice we didn't drop the A because the F is not a vowel. Okay, so heptafluoride. The F of fluoride is not a vowel. All right, so you can be given the name, write the formula, given the formula, write the name back and forth, back and forth. And so let's take a look at this one. Again, my suggestion first is to write the base name. Okay, and so notice Br, we're used to seeing bromide written after, but Br is written first, then followed by oxygen. That tells you that bromine is the central atom, and being the central atom, guess what? Its name remains bromine. Okay, unlike let's say we could have written I and Br3. Here, bromine follows a central atom. So in this case, this is bromide. Specifically tribromide. But here, bromine is first. Then what follows the bromine is oxygen, which is oxide. So that is our parent name. And then come back and do the prefixes. So we got tri, bromine, and then octoxide. Okay. Compared to iodine, tribromide, because in this case, bromide was attached to the central atom. And in this case here, bromine is the central, in this case, atoms. Note the difference here, okay? Again, that A should have been dropped. But if it's not, I'm not going to be worried about it. Here we got phosphorus and sulfur, which will be sulfide, okay? I know this can be confusing, but you know, watch, look, note the trend. The central atom is always written first, followed by whatever is bonded to the central atoms, okay? And so here, the parent name would be phosphorus, sulfide, okay? Compared to this scenario, SO3, where the sulfur is the central atom. And so its name remains sulfur. Trioxide in an example I just wrote here in the bottom. Okay, note the difference. Sulfur stays sulfur because it is a central atom. And this scenario becomes sulfide because it's not the central atom. So its name is tetraphosphorus heptasulfide. Okay. As in the case here, we got sulfur now, which is the central atom. So it is sulfur is the first name. And then we got oxide, 3 of them. So it becomes sulfur trioxide. Just like sulfur dioxide, carbon dioxide, carbon monoxide. Okay, now you're given the name, write the formula. So you just work it backwards. We got iodine, and there's no prefix, so there's one iodine. And then we got fluoride, which now we can write the base formula. Before we were writing the base name and add the prefix. Now I'm writing the base formula, then I come back to the subscripts. Okay, hexa tells me there's 6. And so its formula would be as follows. IF subscript 6. Okay. I'll break it down. Parent formula, chlorine. Notice it's chlorine. So chlorine is the central atom. It's written first. Okay. And pentoxide, you got oxygen. So there's the parent formula. Then we add the prefixes. Di means 2, so there's 2 chlorines. And penta means 5, which means 5 oxygens. Okay. So notice again, chlorine is the first atom written. So that is the central atom. In fact, there's 2 of them. Okay, and then oxide. So we keep the name chlorine because it is this one of the 2 central atoms. And so there's this formula. Okay. Which is kind of interesting here. Let's think about it. Normally we've been talking about chloride, right? And we know the element by itself, the ion by itself has a -1 charge. But in this case, it's not. It can be a positive. And so if we look at how to figure out how to calculate the oxidation number of chlorine, well, guess what? We can do 2 chlorines, okay, plus the oxygens, there's 5 of them, and still each one has a -2 always would do that, and that equals 0. So we have 2 chlorine minus 10 equals 0. So it's 2 chlorine equals 10. Okay, chlorine equals plus 5. So under these conditions in the structure, chlorine has an oxidation number of a plus 5. It literally is, well, it has an oxidation number of plus 5. We'll leave it at that. Under this formula. All right, so here we got phosphorus and iodine. That's the parent name. To go back and do the prefixes, we got 2 phosphorus and we got 4 iodide, I should say. Okay, and therefore we have diphosphorus tetraiodide. Okay. Notice the other scenario we had earlier where we had iodine was first, followed by, I don't know, I think there were 7 fluorides. So in this case, it was iodine first, because iodine was the central atom and it was written first. In this scenario, iodide is the name because it's written second, and it is attached to the central atom, or in this case, atoms. There's 2 of them. Okay, reminders, prefixes are only for covalent compounds, okay? And Roman numerals are only for variable charge metal compounds, not for the 16. So there's a whole bunch of metals out there that require the Roman numerals so we can distinguish which one we're working with, okay? And then polyatomic ions never change their name. They have their own specific name. From that table, we don't change it. And so, like, for example, this is nitrate ion, not nitrogen oxide. No, okay. Its own name is nitrate. And if we need to use more than one, we use parentheses, okay? We use parentheses with a subscript of the numbers that we need. Try these. See if you come up with what I got there. And if you don't, maybe on Thursday we can bring them to class and we can go over them. So barium chloride, nitrogen dioxide, iron 2 phosphate, I2O4, Ag2SO4, and Ni2S3. Okay, here's the formula. And see if work them through, see if you can come up with the same thing. And like I stated, if you don't bring on Thursday, don't forget the worksheet. The worksheet is very helpful with respect to doing a lot of these problems. That, ladies and gentlemen, is the end of chapter 8. Any questions about that? No? Okay, well, that brings us to chapter 9, which deals with, actually going to deal with the first type of reaction that we are going to work with. And that's an acid-base reaction, neutralization. Well, more on that here in a bit. Okay. But acids and bases. Well, let's talk about the acid first. Now, let me give you a little background behind this. Hydrogen. Okay, let's back up a little bit. Let's talk about the hydrogen atom. We know that the hydrogen atom has 1 valence electron. First element is in group 1, 1A. Okay, simply because it has 1 valence electron, it is not a metal, not a metal. Now, if we look at its electron configuration, it has a 1s1, very first element of the periodic table. Okay, that S, if you recall, that s orbital can handle 2 electrons. So the hydrogen atom can actually pick up another electron. And that fills up that 1s2 orbital. And also because of that, it has a net -1 charge. And so some periodic tables actually put hydrogen not only in group 1a, but they stick it over in group 7a, because remember, everyone in 7a is going to pick up 1 electron. It has that capability. Now, this guy has his own little special name. We call that a hydride. Isn't it? The IDE sound familiar? Chloride, bromide, oxide. You know, those are the elements that all gain or pick up 1 valence electron. Okay. Now, the other aspect about the hydrogen atom is it has having 1 valence electron. Okay, so here we got 1 proton and 2 electrons, net negative. In the case of the element, we got 1 proton plus 1 electron, net 0 charge. That 1 valence electron, like the other metals in group 1, can be lost. And so when it does that, it has a positive charge. So now the 1s orbital is 0. It's empty. It lost that 1 electron. And so I only got 1 proton. So the net charge is 0. Okay. And its name now is a very special name. We call that a proton. Okay. A proton is a hydrogen atom that has lost its electron. Okay. And that is what we contribute to the acidity. That is what is roaming around in your stomach right now with the acid of hydrochloric acid. Okay. Now, earlier we talked about the difference between ionic compounds and covalent compounds. I stated that ionic compounds had a bond like magnets. And when they were immersed in water, dissolved in water, they would dissociate and break apart into their respective ions. They have a full positive and a full negative. Some ionic compounds dissociate 100%. We're going to learn about this too. Some of them may be much less, but they all will dissociate some ions into solutions, okay? Covalent compounds share electrons, as I stated, and therefore do not dissociate. And I did state except for one exception, and those are covalent bonded acids, things like hydrochloric acid, okay? Hydrochloric acid, that's a covalent compound, but because of the nature of the beast, it is an acid, and you will find that the first atom is written as H is a good indication you're working with an acid. When they dissociate in water, they produce a proton, which makes it acidic, okay? And so anything that produces a proton in solution, and when we're talking about solution, acids and bases, we're dealing with water solutions, AKA aqueous solutions, aqueous systems. Now, when protons are in ions, protons are in solution, we have an acid. Now, acids, as you know, have a sour taste. Lemon, sour, grapefruit, sour, vinegar, very sour taste, okay? From a chemical perspective, they can be very, very corrosive. They are corrosive, okay? And to determine whether an aqueous solution is acid or base, we have a paper called litmus paper. There's two colors, blue and red. A blue litmus paper, if I dunk it in a solution, a liquid, and if that blue solution litmus paper turns red, that tells me it is an acid. Doesn't tell me the magnitude, how strong it is. It just tells me it's an acid. We're going to learn there's different strengths of acids down the road here. A base. Now, doesn't this polyatomic ion look familiar? The hydroxide. Okay. The hydroxide, any compound that when put in solution, and since it's a hydroxide, as a general name, I could say that any compound, any ionic compound that produces a hydroxide in solution is classified as a base. Okay. I wouldn't taste them, but if you wanted to, they're bitter, and the solids are kind of chalky. Okay. They feel in your fingers, they feel soapy. And the reason they do that is because they actually are denaturing your tissue. The sodium hydroxide. If you have liquid Drano, for example, at home, you ever use that and got that in your hand, it feels slimy. That liquid Drano, what it's doing is breaking down the tissue of your finger. So wash it off immediately. So that's the sliminess, okay? The soapy, slippery. The red litmus paper, if it turns blue, then you have a base, okay? Litmus paper is just simply an on and off switch. It's either an acid or a base. It doesn't tell you anything other than that, okay? All right, now, we have two definitions of acids and bases, okay? And we have a scientist named Arrhenius who defined an acid and a base. Now, by the Arrhenius definition, any acid that produces a proton in aqueous solutions is an acid. And this example we have is hydrochloric acid found in your stomach. There's a number of different acids. We'll touch on those here in a bit. But when they go in solution, they break apart, okay? They dissociate and they form the proton and the chloride ion, okay? That is an Arrhenius acid. With respect to a base, Arrhenius base, it is any compound that when dissolved in water in aqueous system, dissociates to produce the hydroxide ion, okay? So sodium hydroxide, which is what you find in liquid plumber, is a base, very, very alkaline in nature, okay? A lot of skin products use a base. The idea is to kind of scrape off light alkaline to wash off and to get rid of dead skin and so forth, dissolve dead skin. You'd be surprised the chemicals we utilize all around us. All right, so let me clear this up. So that's by definition, Arrhenius acid and a base. Arrhenius acid produces a proton, Arrhenius base produces a hydroxide. We're going to learn here in a bit, there's a second definition because an acid a base does not necessarily have to do anything with hydroxide. So this definition, Arrhenius definition, was very limited. The other definition kind of broadened the definition of bases, okay? So here's your first chemical reaction. There are 6 of them, okay? If you drove today, you did another one called combustion reaction when you burn your hydrocarbons. This one is called a neutralization reaction, okay? And so, for example, is a base. My stomach is an acid. In my stomach, I carry hydrochloric acid. So by chewing an acid, I have a base. And then it reacts with the acid in my stomach to kind of reduce the concentration of the acidity, okay? Now, here's the thing about a neutralization reaction. When you react any acid and any base, you always get water. So here's the thing. Proton plus the hydroxide ion react to form water. So you are neutralizing the acid by adding base, or you're neutralizing the base by adding acid, okay? And so give this some thought. If you're drinking alkaline water, which has alkaline, it's a base, and you ingest it, and it reacts with the acid in your stomach, guess what happened to your alkaline water? You just neutralized it, okay? All right, and you also form, when you have an acid-base reaction, what's called a salt. And let me break it down further so you can see what's happening here. Here's the proton from the acid reacting with the hydroxide from the base to give you water, H2O. Okay. The cation of the base then combines with the anion of the acid to form sodium chloride, to form an ionic compound. We call it a salt, and we tend to think salt is just simply sodium chloride, but remember, in chemistry, a salt is any ionic compound, which is a metal plus a non-metal. Okay, so it's not just defined as sodium chloride. You got potassium chloride, potassium bromide, any metal, non-metal combination is considered as a salt. So that is our neutralization reaction. So that definition, as far as the base, kind of, it was a narrow definition. So a second definition came about called the Bronsted-Lowry base. Now, with respect to an acid, no matter how you look at it, tomato, you're making a proton. Okay. Bronsted-Lowry says an acid is a proton donor, any chemical that produces or donates a proton. But what you're doing, you're creating a proton, okay? Whether you're dissolving it and making it, either way. So I think in both cases, they're both Bronsted-Lowry and Arrhenius acid, both of them protons, same scenario. Where they differ is how they define a base. And a Bronsted-Lowry, whereas Arrhenius base is anything that produces a hydroxide. Remember that. Where Bronsted-Lowry is a base is defined as any chemical compound that accepts that proton that was created. Okay, it is the proton accept. So that immediately opened up a lot of bases that had nothing to do with hydroxide. And how does that happen? Well, let's think about this for a moment. Remember when we did the Lewis dot structure for ammonia? We're going to look at ammonia here. Let me change my color for a second. Ammonia. When we did that, we ended up with this formula. We had a lone pair on the nitrogen, and then we had the 3 hydrogens bonded to that, okay? And then they also kind of showed it in the, kind of like an orbital where the lone pair were sitting, okay? Earlier, I talked to you about a proton. The proton, its orbit, its 1s orbit is empty. So that 1 electron is empty. Got a positive charge here. Remember that, okay? Well, guess what? The lone pair on the nitrogen can take those 2 lone pair. I mean, the lone pair of the lone pair of the nitrogen of ammonia can then combine with the empty orbital of the proton and combine to make a bond. And in fact, if you remember, we did the electron configuration for this ammonium ion. Remember that? Okay. And what's happening here, literally that any other than hydroxide, anything other than hydroxide, and the hydroxide is also included, that has lone pairs that accept the protons is considered a Bronsted-Lowry. You know, even the hydroxide does it. If we look at the Lewis dot structure for hydroxide, because even by definition, the lone pair, okay, one of these lone pair right there, can do the same thing, okay, to form guess what? H2O. Okay. The difference is this: with the Arrhenius reaction, the base reacts with the acid, acid to form water, and the Brownstein-Lowry, the base interacts with the proton to form a salt. Okay, and literally neutralizes the proton. But in both cases, if you think about it, we got the proton with an empty orbital interacting with the electrons of the base. Okay. And in both cases, they're both being neutralized. But the Brownstein-Lowry allowed now a lot more different compounds to be classified as bases, whereas before there was kind of narrow, with the base only being defined as any compound that produces a hydroxide. Okay, so that is the main difference between the two. So the ammonia here gains the proton, and obviously hydrochloric acid is producing a proton, losing a proton, either way you look at it. All right, so, all right, I tell you what, let me stop here because I see the time. And make note of this. We are on slide 7.